Welcome back to the review exercises portion of our coverage of Chapter 12, the regression line. Our first problem asks us to find the regression equation for predicting final score from midterm score based on the information laid out. There's a couple of steps to solving this problem. First, we want to remember that our target is to find the regression equation. And the regression equation has the basic format: y equals the intercept plus the slope times x. So first, let's address let's recognize we have to get a couple of values here. The first one we're going to look at is getting the value of the slope. As we previously discussed, the slope, b, is equal to r times the standard deviation of y over the standard deviation of x. I just want to point out, because we have had a couple of different equations where we've got r paired with the standard deviation of y, and there's nothing magical about pairing r with y. Technically, another appropriate way to write this equation mathematically would be equals r times the ratio of the standard deviation of y over the standard deviation of x. We just are moving the r up to the top because that's mathematically what happens in this context. So just a point of clarification, I got some questions about that earlier. So we can plug in some values here into our basic equation. We've got our value is 0.06, our standard deviation of y. And let's remember that we want to predict final score. So final score is going to be y, average midterm score is x. Then our standard deviation then for y is 20. And the standard deviation of x is 10. So we end up with a slope of 1.2 final points per midterm point. As the values here. So in our eventual constructing of our regression equation, we're halfway there. We're going to have a 1.2 times x here for our slope. But we still need to find our intercept. To find the intercept, we're going to take our average final score minus the slope times the midterm score. So that would be our average final score Why is this a negative here? Because the average final score is, excuse me, is lower than the average midterm score. And if we put this into a sort of equation model, which you don't have to, but if you find it helpful to think about it that way, this would be the mean of y minus the slope times the mean of X. So if you find that helpful, there's a general overview or a general equation you can use in this case. And if we work this out, we find that the intercept is negative 29. Now, you might be thinking, well, that intercept doesn't make sense. How could there be a value, a final score of negative 29? Well, there can't be, and logic tells us that this intercept is not important or isn't useful in the context of our data. And sometimes it is the case that the y-intercept is meaningful in the data, and sometimes it's not meaningful. It's just needed mathematically. And this is one of those times. So we can plug in our intercept here. And we've got a general regression equation for predicting final score from midterm score. And I put a little y hat here because that is telling us this is our prediction equation. Okay, that sounds good, Amelia. So just to sum up this problem here, we could substitute in values for X to get our predicted outcomes for Y. So we could do that, but we have done that quite a bit. So I know most of you are pretty good at value substitution there. That is actually an important skill in our next unit. In our next problem, we've got men aged 18 to 24 in the Haynes 5 sample, and the regression equation for predicting height from weight is laid out here. We've got our predicted height is equal to the slope of the change times our X variable. Remember, we get Y, X, A, and B. Height is measured in inches and weight is in pounds, okay? And if someone puts on 20 pounds, he will get taller by 20 pounds times the slope. Not quite. The slope means that the 151-pound men are taller on average than the 150-pound men by around 0.0267 inches per pound. Similarly, men who weigh 152 pounds on average are a little taller than the men who weigh 151 pounds, and so on. So we can use our prediction equation only in the way intended here. So it's a little easy. Let's look at our next problem. That was a little harder. A study is made of working couples. The regression equation for predicting the wife's income from the husband's income is laid out below, and we've looked at these data before. Remember, our wife's income is Y. Here we've got our slope. Husband's income is X, and then 24,000 is our intercept. Another investigator solves this equation instead now for husband's income and gets this alternate model for the regression. And now we have a true or false. The second investigator has found the regression equation for predicting husband's income from wife's income. So if you want to compute anything, then you can use these data here, but let's see if we need to in order to evaluate this. So the second investigator has found the regression equation for predicting husband's income times wife's income. Well, this is not a legitimate application here. This is going to be false. There are two regression lines, but the one for predicting husbands from wives has a different slope. The slope is 0.375, and this is actually illustrated in one of our examples in Chapter 10, Section 10.5. Okay, let's see. All right. Okay. So does this make sense? Any questions about how? This is a little bit of a tricky application here, thinking about the slope. You can find the slope using the same method that we used before, where we've got our slope is equal to r times the standard deviation of y over the standard deviation of x. And that's going to look then like 0.25, because we can assume that the correlation he found is correct. It's just that the model is not correct. So we've got our correlation for y, for x and y. And since now the husband's income is the outcome, we'll put in 39,000 here. And we divide that by 26,000. And when you do this, you see that it's equal to 0.375. So it's just basically going back to that same idea of you can find the slope through the correlation and the standard deviations of each variable. Yep, no trick. Let's look at our next problem. Now we have a statistician who's doing a study on a group of undergraduates. On average, these students drink 4 beers a month with a standard deviation of 8. They eat 4 pizzas a month with a standard deviation of 4. There is some positive association between beer and pizza, and the regression equation is, now we'll break this out, but let's see what we're looking for here. We want to predict number of beers based on our number of pizzas. Oops, shoot. I meant to write here. Based on our number of pizzas plus this must be our intercept. Number of pizzas is our x variable. But we've got a statistician who lost the data and forgot the slope of the equation. Can you help him remember the slope? Let's see if we can figure out the slope based on this information. What we can look at is we can go back to the idea that the regression line has to go through the point of averages. So the point of averages is the point where the average number of beers intersects the average number of pizzas. Let's look at what that looks like. And on average, the beers our 4 with our standard deviation for the beers equal to 8. And our pizza was 4, and the standard deviation for pizza of 4. So our value, our average for pizza is 4. We know that's 4 here. And at some point here, it's going to encounter the average for beer, and that will happen when beer is also equal to 4 beers. Because the graphs always intersect at the point of averages. And the regression line has to go through the point of averages. So now we've got 1 point, and we could get another point by remembering that we have the intercept right here. Oh, there we go. We have the intercept being the value of y when the excuse me, the y-intercept is the value of y when x is 0. Sorry. So we can make this a point. The y-intercept is a value of y, so we know that the corresponding value of x would be 0, and then the point is 0, 2. So when x is 0, y is 2, which puts our point right here. And we've got a regression line through our 2 points. And 2 points are all we need to get the slope. And I know we've done this a few times, and you can see from this that as x goes up, draw in our rise and run here. So our run is 4 with a rise of 2. So b is equal to the rise over the run. And for every rise of 2 units of beer, we have a run of 4 units of pizza, giving us a slope of 0.5. Does that make sense? Okay, let's take a look at our next problem. Now we've got a hypothetical large study of the relationship between parental income and the IQs of their children. And we've got some data laid out. You can see we've got all the relevant descriptive information that we would like. Obviously, there should be zeros here. I don't know what happened to them. For each income group, the average IQ of children with parental income in that group was calculated and then plotted above the midpoint of the group. It was found that the points on this graph followed a straight line very closely. The slope of the line in IQ points per dollar, quite a unit, and we've got several options here. So let's first think about what's going on here. what they're really asking us is to come up with the slope of the line based on a description of the regression line. So they've given us a description of the regression line, and we need to use that. We need to recognize that this is the regression line of IQ on parental income. Remember, this being X and Y. And we can use these information to, for example, plot out the regression equation or to find the slope. We can remember that our slope is R times the standard deviation of Y over the standard deviation of X. And by now you're probably getting deja vu about this, but I think this is our last problem where we'll practice this one last time. So I've got it, our correlation here is 0.5, and a standard deviation of Y is $15,000, or $15,000. It's 15. They just have it lined up weird. That's what happened to the zeros. They shouldn't be there, but these data, the lineup is a little odd to the eye, that is. And so our standard deviation is 15. That makes sense because we know IQ has a mean of 100 and a standard deviation of 15, because we've looked at IQ data multiple times already. And we'll put that over our standard deviation of X, which was 45,000. So now we can go through and just figure out our slope here and use that information to select the most appropriate option from those available. Oops. When we do this, we see that we end up with, we end up with a slope of 1 out of 6,000. We should always ask ourselves, does this result make sense? Well, I would say this makes sense here because we would expect that the ratio of IQ points to dollars to be a really small ratio because they've got, $90,000 being the average income, whereas the average IQ is only 100. So that's smaller already by a factor of 1,000 or 3 factors of 10, So we would expect that to be reflected in our slope. So our final problem for regression looks at another hypothetical where we've got a congressional report discussing the relationship between income of parents and educational attainment of their daughters. The data are from a sample of families with daughters aged 18 to 24. Average parental income is $79,300. And the average educational attainment of the daughters is 12.7 years of schooling. And we've got a correlation of 0.37. Here, the regression line for predicting daughters' education is spelled out for us. And it's reported as y equals, in our general format for a line, mx plus b, where parental income is x, predicted education is y. We've got a slope here that's extremely small, number of years per dollar, and intercept of 10.3 years. You can see it spelled out here, y, b, x. Oh, B or M. I guess you notice how they do switch back and forth in the book. You should be comfortable looking at that either way. And finally here, we've got the intercept. We'll just label it. Now they're asking us, is something wrong with this equation? Do we need more information? So let's look at it. How would we know if something is wrong with the equation? Well, one way is that we know that the regression line has to go through the point of averages. In this case, we can see that, we'll see that the regression line doesn't. And so let's take a look at, we actually just looked at how we can plot out the point of averages. So we have our average educational, the average for X, which was income. And our average for Y, education, was 12.7. And just like we used in the previous problem, we used these data to plot the point of averages. If we plot this out, which we're not going to do for time purposes, but if we went through and plotted this out in both ways, we plot the point of averages, and then alternately use predict the regression equation to plot our line, we should see that the regression equation as laid out would go through the point of averages. When plotted, this equation doesn't. But it's quite simply to see this, if you can't tell just from looking at this that something is wrong here, we can see that just through basic, using the equation to get some predicted values of Y for X. We get 2 points, plot them through the line, and then look and see if it goes through the point of averages. And so our predicted regression line will go through, say it looks like this, approximately. Our point of averages is not going to lay on the line. So for example, it might be above or below, but the point of averages always lays on the line. So if your line doesn't go through the point of averages, you know something is wrong. Okay, so do we have any final questions on the topics we looked at for regression? The most important problems that we looked at in terms of things you should feel comfortable doing for the exam. Certainly you should be able to find a slope using this model, the regression information and the standard deviation. You should be able to write the regression equation given some data, and use the regression equation to predict values of Y. And given this other information, to remember that you can use the point of averages to help you find the slope, which is still going to go back to the same idea of the rise over the run for the slope.